Yeah. So this presentation, this webinar is going to be about fiction to reality. So I'm going to use two main examples, and I'll change a little bit the content of the presentation because we haven't added some new features in BindLab. So it's nice to use these new features for webinars. Um, what is going to be the agenda? First, I'm gonna spend perhaps a little bit more than half of the webinar on the House of Dynamite. Perhaps you have seen this movie on Netflix, and so it's about an attack on the U.S. side, and so just for I don't know if it's credible or not, but at the end of the day, it's quite technical, and so it's a nice example to create some networks, right? So we're gonna spend some time on this, and after that we are going to focus on another topic, which is also based on nuclear problems. So, but for accident in marine nuclear power plants. So, two different types of examples. And so the first one, again, on the House of Dynamite. So I'm going to spend a few minutes on the new workflow, because now we have very comprehensive ecosystem in Bayesian. So I'm going to create graphs, so not Bayesian network, but I'm going to start to generate a knowledge graph to understand or to show you information about this movie if you did not see this movie, right? Then I'm going to augment the knowledge graph to focus on a specific node, the ICBM node. Then I'm going to have more information on this specific dimension. And then I'm going to create a semantic flow chart just based on the linear scenario, just to give you really the details of the action there. Right? After that, we're going to switch to Bayesian Lab and create Bayesian networks. And this is where I'm going to introduce a new feature. So this is what we call the automatic Bayesian network generator. It's a constraint-free generator. And for illustrating how it works, I'm going to use three different reports that have been generated based on the scenario of the Hearts of Dynamite. And I'm going to also show you the conversational network modeler that will allow me to do some kind of parameter refinement. Then I'm going to generate Risk-Centric Causal Network based on these three reports. So it was supposed to be the main topic, but here it's, at the end of the day, it's kind of reduced the importance of this topic. And then I'm going to again use the automatic Bayesian network generator, but focusing on the nodes that have been generated by the risk-centric causal network. Right? So it's going to be another view of the nodes, the dimensions that have been selected in the risk-centric causal network, which is, as you probably remember, a kind of probabilistic bow tie. And the second part of this webinar, again, will be on this nuclear accident in marine nuclear power plants. And I'm going to still use the automatic Bayesian network generator to create a graph that will really focus on this topic, but just by using the implicit LLM knowledge, which means that I'm going to start by not using the article that is on the right. And then I'm going to conclude the webinar by showing how it changes when we inject or when we use the article as a context, right? So I'm going to use the article and as a basis for generating a causal Bayesian network. So as you can see, we have lots of things to cover. And I want first to remind the workflow we are using now in Bayesian. So we are obviously focused on Bayesian networks. So this is a directed acyclic graph where you have the nodes that represent the dimension of the domain. You have the links that represent either correlation or causalities. And then we have also probabilities that are associated with the nodes. And once we have a fully specified Bayesian network, we have a compact representation of the joint probability distribution of the domain, which allow us to have to define, if we want, the brain of our probabilistic expert system. Right? We have now three ways to create this network. So historically, we have created Bayesian because we were doing research in machine learning. So we were one of the first one to create or to invent machine learning algorithm for being able to use data for creating Bayesian networks, so the structure and the parameters. We are also doing lots of brainstorming sessions. So this allows us to capture the knowledge of the experts and to create manually, if you want, Bayesian networks. And now we can also use LLM. So this is our subject matter assistant that is called Helixia, and that allows us to use the knowledge that has been learned in the deep neural network and extract it, so go from a black box to a crystal box and create Bayesian networks by using the information that is contained in these deep neural networks, right? And at the end of the day, we can mix these three sources of knowledge. And once we have a fully specified Bayesian network, as I said, we have a probabilistic expert system that we can use for decision support, right? So we can do simulation, we can do diagnosis, we can do optimization, we can analyze the domain that we have represented with this network, and we can obviously do risk management because we are modeling probability. And so this is done via Bayesian. So this is our flagship product. So this is for the modeling and so on. And we have also the web simulator that allow us to, share the models with the peers because you don't need to have Bayesian. You can just connect on the web simulator and carry out simulation and so on, right? But since a few months, we have also developed Helix Map. So it's another tool that is not entirely 100% dedicated to Bayesian network. It's a tool for graphs, right? So with Helix Map, we can also generate knowledge graphs, semantic flowchart, causal semantic diagrams, so other type of graphs, so not necessarily acyclic. And so it's a very useful platform for also, obviously, manipulating Bayesian network. But so this is a tool for knowledge interpretation. So you can visualize them, you can explore them, and at the end of the day, you can really easily share the graph with your colleagues, right? So, as I said, the first part of this presentation is about the movie The House of Dynamite. So I hope you have seen it, otherwise you are going to be a little bit spoiled. But anyway, so here, what I've done is I've generated, so I've used LLM for generating a detailed scenario of this movie, right? So I don't remember Gemini or GPT, but anyway. So I have this detailed scenario, and I use this one for creating a knowledge graph, right? So here, this is what you see here. This is Helix Map. So this is when you have an account, so you can freely connect to this platform. You just sign in, and then you will be able to see all the public models that have been published there. So you have different types of models, public, private, and work in progress. And so you have this visualization of the different models that are there, and you can not only see the models that are here, but you can also you see the green button on the upper left corner allows you to create new graphs. So this is what I'm gonna do here. So I'm gonna create a new graph where, so when you do that, you have three ways to create new graphs. So either you have an open-ended question, or you can also associate a document. And the last one is to import an XBL file, so a Bayesian network, right? So, but let's suppose that here I'm going to use a scenario. So it's a document analysis. So I just have to upload the file here, choosing the file in my here. And then I'm choosing the LLM. So you see, we have a large list of LLMs that are available uh, for this tool. I'm going to use Gemini 3 and different types of graphs. So here it's a knowledge graph. So when I validate, I have a new icon there. Sorry. And then while it's generating the graph, I'm just waiting for the result. And after a while, we have here everything is updated, and then I can have access, display the graph, right? So here I'm gonna directly click on this link and switch to Helix Maps. So this is now the graph that has been generated. So I can expand here. Perhaps I just gonna sign it just to be sure. that everything is going to be okay. Okay. And now go back, click here. All right. So now I just do, I can display the node with simple badge disk. So this is like in Bayesian Lab, simple badge. So same thing. And here, this is badges, but with the comments. We have different layout algorithm. So I'm going to just use here elk vertical. And then I have this new layout, right? Uh, it's probably a little bit too small. So I'm going to just switch to simple badge and then hide this toolbar and focus here and display it again because I forgot to do that. And I can also on the arc, I can also show, because this is a knowledge graph. So we have entities. So the first one is a house of dynamite. We know that this is a 2025 thriller film directed by Catherine Bigelow. So we see that she's here, right? Then we have also the who wrote the scenario. Then we have the different actors. We have the year here. We have the president that is here. So let me focus now a little bit there. So you can just zoom in, zoom out very easily. So if you have seen the film, you will recognize that we have the president that has the nuclear football here. It's a black briefcase where he's gonna select what is gonna be the nuclear retaliation options. And then we have Secretary Wright Baker here that is located in the Pentagon. So this is where they're gonna here Raven Rock. This is a bunker, and we have here the ICBM. So this is for intercontinental ballistic missile. So this is the node where now I'm gonna focus on just to have more information about this missile, right? So I go back to my slides and I'm gonna augment this graph. So this is one nice feature. So I have generated a knowledge graph, but I can also select a node and build upon this graph another one, right? So here I just have to make a right click on the ICBM node, select Helixia, and then I know that I have the selected nodes here. So I just have to know what's going to be the question. So to build the question, I can just use a label. I can also select to use a short description that is associated with this node or the description. So here I'm just going to use the label because it's informative enough in this context. I'm going to associate a linear scenario and then build, select again Gemini 3 and select the option augment existing graph. So which means that I'm going to create a knowledge graph that will focus on ICBM using the file, the linear scenario, and then create a graph that will mix two knowledge graphs if you want. Right? So this is again running, and then I can have a look at my network. Bring back this tool. So same thing. I will activate the layout algorithm. And here I have also some tools that allows me, because we have, as in Bayesian Lab, we have classes that are associated with the nodes. So I can also focus on the nodes, on the classes. So if I select the chunk 00, which this means that these are the nodes that have been generated in the first knowledge graph, right? So this is exactly the graph I had before. And now if I focus on generated one, so this is the augmentation, if you will, right? So here I have a node, a graph that will contain all the nodes that have been generated in the second iteration, right? So now if I double click on ICBM, well, I will bring back everything else. If I double click on ICBM, this is exactly equivalent as making a right click here and selecting neighborhood. So if I double click, I'm focusing on the neighborhood of ICBM, which means just the direct ascendant and descendant, right? So with this ICBM, so this intercontinental ballistic missile, we have NORAD here that tracks this missile. We have China that monitors it, Russia that denies to be implied here, and North Korea that is suspected of having launched this missile, right? And this missile has been launched from the Pacific Ocean and targets Chicago. You also see that we have some little icons associated with the nodes with +1 and +2. Here we have 8. So this, when you have an arrow that goes down, this means that there are hidden children, right? So if I double click here, I'm going to see the children that were hidden. If I double click again on the graph, I will show everything else. I'll go back to my target. And now I see that I have also for Russia, I have one hidden parent. So if I double click on it, I'm going to see that this is Secretary Ray Baker that is connected to Russia because it contacts Russia, right? And this one, we see we have one hidden parent and three hidden children. So if I double click on this, I have these neighbors, right? So we have, when we double click like that, as I said, we are using this function. And when you select this one by using the right click, you can choose a radius and you can also choose the layout algorithm you want to use for focusing on the neighborhood of a node. Right? And again, if you double click on the graph, you go back to the full picture. Right? So now let's switch to the linear scenario. So the first one was really the detailed scenario, describing exactly how the movie is organized. But at the end of the day, if you have seen the movie, you probably remember that we are seeing 3 times the same thing, but with different angles. So here, this is really from linear, right? From we have 18 minutes at the end of the day. The movie represents 18 minutes. So we go from minutes 18 to 0. So when I create now, I'm going to create a semantic flowchart with that. So for creating a semantic flowchart with the document, I need to go through the open-ended question. And the reason for that is because we can also upload more than one file. And so it does not make real sense to create semantic flowchart when you have a large set of documents, because then there is no real flow, right? So here I just have one, so I'm gonna enter my question, house of dynamite, select my linear scenario, and then again my engine. I'm selecting, here are the type of graphs that I can use. I'm gonna select the semantic flowchart, and then click on generate and return to workspace. So this is my workspace. And now the network is ready. Just have to click on this link to show it. And we have, so if I do that, we have the different steps in this movie, right? And let's see now, I think I can use the badges. It's good enough. And you see, so we start with 18 minutes before T. So where US satellite thermal sensor detect a high intensity heat signature, right? And then there is trajectory confirmation, and DEFCON escalation, interception attempt, defense failure, public warning in Chicago, different houses. Stefan, I can hear you. I can hear you. Okay. Presidential options, and then the final resolution, right? So this is a semantic flowchart. So if you want a semantic flowchart, it's the same thing as a knowledge graph, but in the knowledge graph, you have entities and connection, and this connection can be any kind of relationship. It can be belongs to or is part of and things like that. But here it's like a knowledge graph where we focus only on temporal relationships, right? Now, let's continue with the third part where, based on still on this house of dynamite, I've used Gemini for generating a risk analysis report, right? So it's a 4 pages report. Then this LLM proposed me to, if I were interested in having an after action report. So I said, why not? I don't know exactly what it is because I'm not part of the army. And then there was also a target discrimination report. So I have generating these 3 reports. So obviously he has to to guess what happened at the end of the movie, even though when the movie ends and we don't know how it ends. But here, so this one has speculated the outcome, if you will. So I'm gonna use these like 7, 9 pages, right? And I'm gonna use a new feature I was mentioning in the introduction to create a Bayesian network really that focus on these three reports, right? So for that, I just go to the home page, click in this new tool. So this is really so almost well, we use the same icon. We change the icon of the causal network generator and reuse the other one for the new feature. And then here I just have to enter my question. So it's going to be a risk analysis. Then advanced mode, I'm choosing my engine. Then I have associated the three reports in one document. And so this tool will really build a Bayesian network, but without any constraint. So what I mean with constraint is with the risk-centric causal network or the causal network, we have some constraint on the structure or on the role of the nodes. Like, we want to find what are the confounders, the interventions, and so on. So here there is absolutely no constraint. And so we run this tool, and after a few minutes, because it's not that fast, we have this network that has been generated, right? So you have colors, which means that when you have colors, we have classes. And so here what is really nice is that in all the other networks that we are generating, we are usually working with proposition, which means it's either true or false, because then we are, asking for causal effect, and we are using dual noisier and some very specific function for, building the conditional probabilities. So here we don't have this constraint anymore. So we can have any type of node, right? So it can be discrete, it can be continuous, can be utility function, it can be decision node, it can be anything, right? And then, so here I have a node with that allows me to identify what is the threat origin. And then, as you can see, we have also nodes that have three states, at least one here, the event outcome. And then, so we have comments that are associated with the links. We have, the executive summary of the network that is associated with the comment of the network, right? So in HTML. And then we have the classes, which would come on. Oops. My classes. I'm gonna have classes there, right? So same thing, no constraint on these classes, so they have been automatically discovered. And then I'm gonna use helix map now to explore this graph, right? So I go to the tools menu and select publish to helix map. And then I can click on the link and get my network here. So for this one, I think I can do that. And so in this network, you see the origin of the threat, so that defines the warning time. So you have the comment associated with the link here. So the warning time will have a causal effect on the comment response. And the same thing with the attribution status. And then you have this depends if it's coming from a submarine, you have less time than if it's coming from a silo. So this has an impact on the shot doctrine. So you have the reliability of the interceptors, right? So that depends. So this one is a gray node, so which means it's a latent variable that has been used for divorcing the parents of interception success. So you have this latent variable here. Then you have the threat sophistication. So is it using decoys or not? So this has an impact on the sensor discriminations that will, at the end of the day, have also an impact on the success, right? And then on that, you have the outcome of the event. And here, this is where these reports are speculating, because perhaps it will not detonate, or it's a dud or dude. I don't know how you pronounce that. So this is the unconstrained Bayesian network. And then now I'm gonna, because everything has been built, but as always, you always need to check, because this has been generated with Helixia, but we know that we can have hallucination, we can have mistakes, so always check what you have, right? So we are gonna do that via some, you know, interactive scenario, right? So here I'm gonna just say, what if the outcome is safe? So I double click on save, and I can see, you see with the gray arrows, what is the impact of this observation, right? So it's Bayesian inference here, so it's like diagnosis. So I know the output is safe, then I can see that interception success is kill, 100%. So no uncertainty, obviously, it makes sense. So then, come on, we have the sensor discrimination that is effective. And this one, we have still 55% of low probability. So that does not seem right, right? So the idea will be perhaps to check, or look at the table here. And so we go back to modeling and double click on the node, and we have this table where we see that when the shot doctrine is degraded, it's 100% low probability, but when it's optimized and there is a malfunction, we still have 60% of high probability, which does not make real sense, right? So what I'm going to do here, I just select the node, right, and go to Helixia, and I'm going to use the conversational network modeler, which is a new feature that will try to fix this. So I just have to enter, it's like a prompt, if you will. So I'm going to say, well, fix this conditional probability table. Right? And then I can go back to advanced mode, because I don't need to resend the document, because everything is already contained in the network. And then I'm going to just have to wait a little bit. And after that, I'm going to have a new probability table that has been fixed, right? And now if we go back to validation, we can see if it makes more sense. So when I have malfunction now I have 100% of low probability, which is much more sense than before, right? And now let's suppose that I say, oh, but perhaps I have high probability, low probability, but perhaps it would be better to have another state like zero probability. So I'm going to just use the tool, so the conversational network modeler, for adding a third state, right? I go there, and here I just say add a third state for zero probabilities and fix the conditional probability table, right? And then I do that, I wait a little bit, and after a while, I'm going to have a third state that has been added to the latent variable kinetic solution. I'm going to have a new probability table, obviously, and it makes perfect sense when we look at that, because now if the interception is in malfunction, then we have 100% of zero probabilities, and the low probability is associated with functional interceptor and degraded shot doctrine, right? So now if I go back to this table, because this one has also been updated since we have a third state, so we see that when it's zero probability, obviously, we have 100% of chance to miss the missile. All right? So now I go back to validation mode to carry out inference and go through some plausibility checks. So I go back and say, okay, now it's safe. I see 100% of priority that we have killed. Then we see also that interceptor reliability is functional, right? So much better than before. If I remove this one and set malfunction, I can see that we have this zero probability, and then we are sure that we are not going to be safe. And now, if I just do another type of what if scenario where I'm just now observing, the threat origin. So I say, what if it's an ICBM, right? So from a silo, then we see that the warning time is standard one, so more than 30 minutes. This has an impact on the fact that the shot doctrine is optimized. And we have then a high probability of associated with the kinetic solution. If we have a simple warhead, it's going to be better, right? Because the sensor discrimination is going to be 96% effective, effective with 96% of chance, more precisely. And we have almost 80% of chance to intercept the missile, right? And then 80% of chance to be safe. Now, if we simulate with a submarine, so the missile has been launched from a submarine, so we see that we have a compressed, so it's less than 20 minutes for the warning time. Then we can see that the command response has been impacted with almost 82% of paralysis hesitation. We have a degraded shot doctrine, and then even though the interceptor, well, here with the command, okay, I wanted to go back, but I cannot. Who knows why? Okay, anyway, so if I say it's safe, well, did I go back to the beginning? Okay, no, not good. Yeah, so functionals, we have this, so if this is coming from a submarine and the interceptor reliability is functional, we have 60% of chance to have a high priority kinetic solution. And since it's a simple warhead, we have also almost 56% of chance to kill the missile, right? And then to be safe. So now it was a kind of simple network. So let's go and again use the same tool, but try to generate a more comprehensive model. Right? So I will use the same tool, but now instead of just risk analysis, I said comprehensive risk analysis with 20, 30 nodes. Right? So this is my prompt here. I do OK. And so by using the same document, I have now this more complex network. So I can go to sanity check. Since it's more complex, chances are that we can have some mistakes, right? So, and I can see here that I have a warning that is associated with the global stability. And if we double click on this node, we are going to see that we have no probability. So the table was perhaps too big, or the LLM was lost during the generation of the network. So we are going to have to fix that. So we use, again, the conversational network modeler for fixing this conditional probability table. Right? So we wait a little bit, and now everything is fixed. We go to Elixmap for just having a quick view on the structure. So this is my network, so I can try with badges like that and see if it makes sense. So perhaps we can just go here. Better. Oops. Okay, so in this network we have I need to display this one. Yes. All right. So we have three nodes in red here. So this is for again the source of the missile, the trajectory, and then this has an impact on the decision time window. That will have an impact on the decision maker status. That depends on the attacker identification, and this one has an impact on the global stability, right? Because with uncertainty we have chaos, obviously. Then we have here the protocol. We have the interceptor release authority that will define the engagement status. So the decision time window has also a causal impact on the warning time, for the population. We have the same thing for the missile. So the environment, is it in atmosphere or in space? The target discrimination, the countermeasure, here the health of the interceptor, then the warhead functionality, the impact, and then the human cost, right? So if we go back now to Bayesian Lab, we are going to see we carry out inference and we use again interactive scenarios. And in this one, I'm just going to say, well, what if it's launched from a submarine or from a silo first? Then I can see that this has an impact on the trajectory, which is a 70% chance of being standard. The decision time window is more than 30 minutes. And then we have the population status is 70% standardized or sheltered, sorry. And here, human cost, you have the distribution with the three states. If I switch to the submarine, then it's the trajectory is depressed, and we have the decision time window that is less than 20 minutes. This has an impact on the population status that is now exposed with almost 88% of chance or risk, more precisely, because the cost is increasing. Then we have here on the green nodes are for the identification of the attacker. And then that has an impact on the decision maker status. And just by playing with that, so setting evidence, we can see and check if the network makes sense or not, even though obviously in real life, you will have to go through each CPT one by one and check with experts if it's correct or not, obviously, and change it and probably edit them, right? But this is a very good starting point because this is the kind of network that really usually needs more or less 3 days to create this kind of graph. Okay, so this is for estimating the impact of the retaliatory decision, so on the global stability. Right, and now, so this is what was supposed to be the heart of the presentation. So I'm just going to still create one, so a risk-centric causal network. So, but since I've already done 2 webinars on this topic, I think if you are really interested in this kind of graph, you can go back to the recorded version of the webinar. So here, a risk-centric causal network, it's like a probabilistic bow tie. So it's a constraint network where we have the target, so the main risk. Then we have the threats, and we have the preventive barriers, we have the sub-risk, we have the consequences, and we have the mitigating barrier. Each of these nodes have a specific color. And here is how it works. We go just to Helixia and document analysis, causal network. So this is a constraint-driven causal network generation, which select our LLM. Here I'm choosing GPT 5.2. It's checked risk-centric causal network. And then we wait a little bit. And we have this network that has been generated, right? Same thing, same workflow. Go to Helix map. It's easier to explore. So I will go there and go to vertical. Usually for the bow tie, it's better to use a horizontal layout, right? And should be okay. No, I go back here. So again, we have the classes here, and I think it's a very nice tool for that because I can really explore this graph with the classes. So I will first start with what are the threats of this of this problem. So we have the SLBM launch detected with extremely compressed timeline. Do we have decoys or not? Mechanical failure or not? And attribution, positive attribution or not, right? So these are the threats, the main threats. Then we have what are the preventive barriers. So this is coming from the scenario, but these green ones are not coming from, they are coming from more or less the three reports, right? Then the threat and the preventive barrier are defining the sub-risk, right? So when you see a red link, this means that this is a negative effect, and a blue link, a positive effect. So the threat has a positive effect on this sub-risk. And you have, as you can see, a coefficient. So the 90 here means that this is a positive effect. So this is a local effect of this driver, right? 90. And these guys in red have a negative effect, minus 80, minus 55. And these coefficients, these effects are used within this conditional probability table or within these nodes by using, we are defining the conditional probability table by using a dual noisy OR, that is using both the negative and positive effects, right? So once we have this sub-risk, we can then add the main risk. So they are just defining what is the main risk, and the same thing here. We have the consequences and the mitigating barriers, right? So same thing. You have, so let me create really a bow tie here, and right. So these consequences, so they have obviously the main risk has an impact on them, and you have the mitigating barrier that will reduce the effect of these consequences. Okay. So now, if we go back to Bayesian, we can, since we have these parameters, we can obviously do inference. But as you can see, this network, all the nodes are propositions, right? So this is like the SBM launch detected with extremely compressed timeline, less than 20 minutes. It's true or false, right? And so all of these nodes have been are like that with true and false. This allows us to estimate local effect and to use these dual noisier functions, right? So if I set true, then I can see that the engagement is delayed with a probability of 80 or 76% or 77%, right? And this has an impact on the main risk. Then if I activate one of the preventive barrier, I can see that the sub-risk is decreasing. Two barriers is decreasing even more, and it has an impact, obviously, on the house of dynamite main risk, right? Same thing there. If I have a problem with a mechanical failure with my interceptor, the sub-risk is increasing to 83%. And then if I activate the preventive barrier, I will decrease this risk, right? And then going to the consequences, if I have here 16 or 17% of chance to have the main risk activated. So setting true for the resilient infrastructure will reduce the risk associated with the critical infrastructure disruption, right? And also the kinetic blast, right? So it's it's a graph that is kind of it comes with lots of hypotheses, right? Because here we are assuming that all the preventive barrier, all the threats are independent, which is probably not the case. Then we have this main risk that is there, but it's like a virtual concept. So we know that this is not perfect at all, right? But it has one advantage: it's like super easy to read, right? Very quickly you can identify what are the threats, the barrier, and so on. So it's a very useful communication tool. But for inference, it's not really the best one, right? But still, so it allows also to make the connection with the probabilistic risk manager with that are using both eyes. So with this kind of approach, they are not lost, right? So this is a good step before switching to a fully specified Bayesian network, right? So now what I'm going to do is I'm going to use the new feature, the automatic Bayesian network generator, but instead of just saying, hey, just create a network based on this document, I want to say you're going to create this, but by using the node that comes from the risk-centric network, right? So I will just go to my network, then data, then export a dictionary of nodes. So it's just a text file where I'm going to have the list of the nodes. And then I will just go to my new feature here and say, you create a risk analysis with these nodes, right? So there is a list of the nodes here along with their comments. And then he will recreate a graph that connects all these nodes. So let's have a look. But now it does not have, the architecture of the bow tie, right? So you have that here. Perhaps I just use the horizontal one. Then do I need to use a short description? It's going to be better like that. And hide this, right? So this is, as you can see, so this is not the bow tie structure, even though the nodes are the same. And there is one thing that makes sense here. So the house of dynamite node, I told you before it was kind of virtual. Here it is not there because it does not mean anything, right? So now the target is this one, kinetic blast and structural damage in Chicago metropolitan area. And it has been impacted by or defined by two latent variables. So the efficacy and of the interception and the defense availability. So let's focus. We see that we have two hidden parents here for the defense availability. So if I double click here, I'm gonna dive into this node, and it is defined by the engagement that is delayed and the terminal defense for Chicago. So, and I can see that this one has also two hidden parents. So go there, and these two parents are latent variables. So we have the engagement is defined by the speed of the decision and the timeline pressure. So if I double click on timeline pressure, I can see that this is because this is coming from a submarine, and this has also an impact. The shot doctrine has an impact on this pressure, right? So if I go back here and see now the decision speed, two hidden parents, the decision paralysis, and the defensive intercept authorization. And this guy has two parents. So I double click on these two to see the preventive barriers here, right? Or was the threat? No, this one. Yes, so this is now the rapid multi-source attribution, right? And this one has an impact also on the ambiguity of the attack, right? So if I double click there, I can see that this is a child of the target node, if you want. And so we have one cause that is the positive attribution, and we have also the impact on the strategic escalation risk. So if I click here, I see that we have the ambiguity plus the crisis stability. And this guy has two parents. And so this depends on the crisis leadership continuity and the political control. If I double click on this political control, I have these two nodes, right? So double clicking on the graph background, I go back to the full picture. And so you see that when you double click like that, you can really explore the graph. So we still need perhaps to find a way not to be lost, because after a few clicks, perhaps you are losing the entire picture of the graph. But well, we are still working on that. And but I think it's quite interesting to have this feature to really focus on the neighborhood and look at this icon, right? So if you have a node where there is no icon, you don't need to double click on it because you will not have any additional information, right? So now we are going to interact with this model. And so we set this kinetic blast as a target node. And then we can obviously carry out what if scenario. So what if it's coming from a submarine or not? Then we have the impact on the timeline pressure, then the shot doctrine. Then we can switch to the defensive intercept authorization, then the procedure, the NC3 procedures. So you see, each time I'm setting evidence, you have this information is propagated in the network, and we are updating all the nodes for which we don't have any evidence, right? So this is really Bayesian inference here. And so you can see that the priority of the target is slightly moving each time I'm setting evidence. And I can go there to the blue one, the terminal defense for Chicago, then to the green one here for so these are mitigating barriers, right? The urban search. So we see that the priority of having an effective immediate response is now 95%, and so on and so forth. So we can go back here for the political decisions and see how it impacts the strategic escalation risk, right? So again, you need to so you can quickly check, what I call here plausibility check is going through this type of inference to see if the probabilities are moving in the right direction. But at the end of the day, if you were to really use this for real, you need to go through each table and check carefully if the probabilities are correct. And the idea is usually to do that with experts, right? So now let's see the second topic. So this is, the idea is to use an article. So it was the original idea to use. So it's an article that has been published last year by Zhao and colleagues, and it's about the cause analysis model of nuclear accident in marine nuclear power plant based on the perspective of socio-technical systems. So a very long title, and so here, what I've done was to say, now that we have these new features, so it was not planned at the beginning, but I just say, what if I'm just entering the title of this article and ask this generator to build a very comprehensive network that answers this question, right? By using just the implicit knowledge of the LLM, which means that right now I'm not using the article. Right? So this is coming from the billions of documents that have been digested by the LLM. And I can see, so I have my executive summary here in HTML. I have different colors, which means that I have different classes. I can see that I have nodes that have 2 states, other 3 states, and I can even see in purple at the very bottom of my network that I have a utility node, right? So even though I did not ask for a utility node, he just added a utility node for measuring the severity of the consequences. So going through the plausibility check, I can go there and say, what if the workload is normal or overload? So we can see the impact on the fatigue level of the crew. Then if the safety culture is strong, so this has an impact on the maintenance quality. Then if the training quality is inadequate, we have an impact on the situation awareness that can be lost here. And then if it's adequate, it has a positive effect and increase the priority of maintain for the situation awareness. If we have a problem with the electrical power, we see that has an impact on the coolant pumps, right? We can see that we have a C condition that has an impact on the pipe integrity, and so on and so forth. So really, so this is my utility node. You can see that it's purple here. The external impact, so if we have a collision, obviously, it can be a problem, and so on, right? And so the target node here, this is the output of the accident. So if I want to, instead of interacting like that with my network, I can also generate a tornado graph, right? So you see, I'm just using the mean value here. So assuming that known is 0, release is 1, and meltdown for the target is equal to 2. And here, let's suppose I just want to create this tornado, but just focusing on the root nodes. So I'm focusing on the root nodes. I'm selecting the root nodes and invert the selection to now associate a cost, so a not observable cost, to all the nodes that are not root, if you will, right? And this time I will just focus on the root. So this is my tornado now, but based on the root nodes, right? So the external impact is the node that has the strongest impact on the target. And now I can also obviously carry out more sophisticated analysis. So I can set, for example, that the output is a meltdown for the nuclear accident. So this is a hard evidence on the output. And then carry out what we call a most relevant explanation analysis with a weight of evidence. Right? So I'm just selecting these settings, and then we have the set of the most relevant explanations. Right. So the most relevant explanation is to have a collision or an attack. The second one is to have, a compromised reactor pressure. And then the third one is a combination of 4 different dimensions. You have the electrical power that is in failure, a poor interface design, inadequate training quality, and overload workload, right? And so on and so forth. So you have a long list of the most relevant explanations. And so the last one I wanted to show you is, what if now I'm using the article, right? So now it's going to focus really on the I don't remember if it's 16 pages or so. So I'm using, again, the constraint-free Bayesian network generator, same prompt, but now I'm associating the article. And then after a few minutes, I have this graph. So you can see it's much more complex, right? And it has extracted all the nodes that had been described in the articles. So if we go to helix map for the last time, we can use this. Perhaps I will just use this way and hide this. So we have in green, so these are the nodes that are related to the crew, right? Attitude, attention, nervous emotion, pressure. So we have the physiology and psychology dimensions, quality and ability. You have the response time, the team communication, team collaboration. So this one is the effectiveness of information exchange. And then in red or pinkish here, you have the political decision. So what policy, you have the research and design institution, regulatory agencies that have an impact on the team communication. And then you have here in orange the technical dimension that have been described in this article, like PAM2, water source number 1, and then you have a different set of valves. And here you have the external marine condition and the offshore operating environment. So this is defining this latent variable. So the ship marine aggregation of marine environmental condition. So this has an impact on the ship environment that is also impacted by the cabin environment. And then, so you have the technical stuff here with the low pressure safety injection system. And all this, at the end of the day, is connected with the severe accident, right? Severe accident. So this is really, if you read the article, you're going to see that it's very close to what they are describing. And then, same thing, plausibility assessment. So we can go through real quick some what if scenarios. So the policy is adequate, the authorization is adequate. We have 90% of regulatory inputs that is strong. Then if the team is collaborating, we have an impact on the green ones. Nervous emotion is high, pressure is high, so we have a high psychological stress here that has, in the end of the day, an impact on all the other ones, right? If the sea is a severe condition, then the cabin is also unfavorable. So we have very unfavorable ship environment that will have an effect on the target, right? So you see a little bit how this is working. And I guess I spent quite a bit of time on the new feature, but I think they are really, really uh, powerful. Right? So if you want to play with Helix map, so you can go there and sign in, and you are going to see all the networks that I've shown you today, plus many others. The simulator, even though today I did not create any simulator, but I created a few yesterday, so you can see other stuff. Uh, and so same thing, you can always connect there and play by yourself. So thank you for your attention.